To a chemist, the most interesting thing about these elements, be they metals, nonmetals, or metalloids, is their ability to combine with one another and form compounds. We represent compounds formulas. We represent the structure of a compound using chemical formulas. These use the chemical symbols, those 1 to 2 letter symbols, to denote the type of atoms in the compound, and we use numeric subscripts to tell us how many of each. Ratios tells how many of each they have. For example, carbon dioxide. We've talked about that before. That would be written with a carbon, an oxygen, there's my 2 symbols. Di, as you probably know, means 2, and we put it down as a subscript. This is written as CO2. Now, carbon dioxide is an interesting species. It is a molecule, which means, for one thing, it's an independent entity. You can isolate one CO2 compound, one CO2 molecule. Right? Molecules, they're 2 or more atoms bonded together. The molecules involve a sharing of electrons from each atom, called covalent bonding. They only have bonding to their adjacent species. Right? In this case, we've got 2 atoms together in B. This is called a diatomic. That means I've got 2 atoms together. All right? Now, you can see here, this is representing the plus is the nucleus. Here. And here is the area where I'm going to find electrons. They are considered to belong to both atom 1 and atom 2. All right? Okay. Now, it's kind of like a tug of war, like these young ladies. Each of the electrons are being pulled by the other's nuclei. Remember, opposites attract. Opposite charges attract. We can get all sorts of different kinds of molecules, and molecules usually involve nonmetals. Now, this may seem to limit us a great deal because there are only 17 of these, but there are millions and millions of molecules that have been identified. Here are some common ones, and notice as I go through, they only involve these 3 elements in 1 or more combinations. Here's oxygen. Oxygen, oxygen. He's written O2. We're going to keep red as oxygen everywhere here. Okay? All right. Over here we've got water. Let's make hydrogens white. Water is always 2 hydrogens, 1 oxygen. The compound is written as H2O. Notice this behaves very uniquely. Water is not the same as 2 hydrogen atoms and 1 oxygen atom. When they combine, they have their own physical and chemical properties. That's important. Let's make carbon black. All right, carbon dioxide. You notice that these little balls indicate shape of the molecule as well. And it is important to note that water is not shaped like the linear carbon dioxide. If it was, it would have vastly different chemical and physical properties. We'll get to that as we go through the quarter. Here's ethanol. This is drinking alcohol. I better say drinking. We don't want you to intake any methanol. That will kill you. But ethanol has the formula C2H6O in its simplest form. All right, here's hydrogen, hydrogen, carbon, carbon, and we can't, can we see? Yeah, we can see him back there. All right. Ethylene glycol. This is the stuff you put in your radiator. Right? He's got the chemical formula. Well, let's see. I've got 2 carbons, 2 oxygens, and you can't see them all, but I have 1, 2, 3, 4, 5, 6 hydrogens. Here is a common species, aspirin. Well, he isn't that big. He is a miracle drug, though. Okay. Now, it's not useful for us to draw these, what these are called, space filling diagrams. Let's look at some other things. All right, let's look at 2 species. This is the name ethyl alcohol, or, you know, chemists aren't happy with one thing, so we're going to put the other name, ethanol. And this guy is methane. These are both called organic molecules. All right. Well, they belong to the organic molecules family. Okay, there's the name. Here's the chemical formula. That's what we had before. Now look at the structural formula. The structural formula is kind of neat because it tries to emphasize the parts of that molecule that make it behave like a member of its class. For example, this is an alcohol. What makes something an alcohol is this oxygen and hydrogen group. All right? We can change this part here. All right? If we have one carbon, it's methanol. 2 carbons, it's ethanol. 3 carbons, it is propanol. 4 carbons, ethanol. Butanol. But they all have this OH group in common. And here he is sticking his little butt right out there. All right, that makes him behave as an alcohol. Well, I don't want to have to draw this structural formula all the time. It is useful in many cases, and if chemistry is anything, it goes for the practical. So instead of writing the chemical formula like this, you'll often see chemists write it like this. C2H5, and then they'll write the OH group explicitly. The alcohol group is written purposefully, explicitly. And you know why? Because there are other chemical species that have this same basic formula that are not alcohols. For example, we could have this guy. H3 and C. Oh, dear. I'm having a little bit of trouble with space here, so I'm sorry. Let's try over here. We could write it as C, O, C, H, 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 H. Okay, now each time you see one of these dashes, that is a covalent bond. Right? That means, oh, and there she is right there. That means there's a pair of electrons sitting right in here. Here is my covalent bond. Let's come up here. These are all covalent bonds involving 2 electrons shared. Okay? All right, shared by, in this case, hydrogen and carbon. All right, now this guy behaves much differently than an alcohol would when you put him into a reaction with other chemicals. All right. Let me draw him one more time, trying to get it going here. H, C, H. All right, so all those hydrogens are attached to carbon. Then carbon's attached to an oxygen. Then the oxygen's also attached to another carbon. And she's got, You can see where my board is having trouble. 3 hydrogens attached to her. Pull this way out, and there she is. All right. Okay. All right. Now, and this is the representation of the space filling. We call that space filling. Ball and stick. These are all down here methane, which has the formula. Can you guess? The central atom comes first there. And then we know that the 4 hydrogens are attached to the carbon, so they're going to come second. All right. Now, another type of bond is the multiple bond. Now, we can only have a single, a double, or a triple. That's as far as we go in nature because of many reasons we're not going to go into here. But we're going to represent them pretty much the same way, that a pair of electrons is represented by either 2 dots, so we could do it like that, and that gets, as you might imagine, quite tedious. So we use a dash to represent a pair of electrons. So here you'll notice you have 4 total electrons in 2 different bonds. And here, can you guess? 2 each. So I've got 6 electrons total. Great. Now what happens if I have 2 species that exchange electrons? They don't share them, they exchange them. When an atom or molecule loses an electron, it becomes positively charged. Why is that? Because now it's got more protons than it does electrons. Remember, we are not doing anything with those protons in the center of the nucleus. We are only working with electrons. Bonding only involves electrons. But I keep harping on this because it's important for you to realize we are doing nothing in the inside of the atom. Or, I'm sorry, the inside of the nucleus. Okay. All right. So, this is true for ionic, molecular, any bonding. Any chemical bonding involves electrons. All right, so sodium. She is sodium. Its symbol is Na11. Okay? And you can find it on the periodic table in the first column. He is definitely a metal. All right. Metals tend to lose electrons. So they tend to form cations. All right, I start off with 11. I end up with 11 protons, but instead, this is like a cross-section of the atom. When I become the ion, I have 1 less electron. Conversely, nonmetals tend to gain electrons. So they become what are called anions. Okay, so let's look at chlorine. Chlorine has a symbol Cl. Oftentimes you'll write it as a script, so you emphasize the L is with C. And he has got 17 protons. He is 17 on our periodic table. He is on the other side of the periodic table in the nonmetals. Right. 17 protons beforehand, 17 after. But look at the electrons. She has gained 1 electron. change from the atom to the ion. Now what happens when these fair things come together? Well, the force of attraction is called an ionic bond, but they are simply opposite charges attracting between the anion and the cation. Remember, this guy is negative, this guy is positive. Ionic compounds, now these are different than molecules, because these are large collections of anions and cations in arrays, lattices, okay? Like bricks piled up on top of one another. All right, they are not discrete units. How about, let me say, single discrete units, like molecules. All right, metals form cations, nonmetals generally form anions, so ionic compounds are usually combinations of metals and nonmetals. This is how we recognize them. Recognition. So this means you have to be able to look at the periodic table and know where the metals and nonmetals are. Well, the one that we come in contact a lot is sodium chloride, table salt. And you see what I mean? We have these long distance arrays or collections of these ions. So here is my Cl minus, and he is bumped next to Na plus. And there is a pattern to these. There is a repeating pattern. And it's based upon many things. Of things. But overall, the solid must be neutral. That means the charges on the anions must balance the charges on the cations. Okay. Charges of anions must balance, be equivalent to charges, oh, I hope I don't mess it up into the bad area, of cations. If there was a net charge, it might discharge on your hand as you poured salt into your hand, and we know that doesn't happen. Let's take a minute to look how beautiful this is. All right, this is the molecular level, and I know we call it molecular level even though it's not a molecule. Well, we're trying to say it's microscopic. How's that? Put it in parentheses. I'm sorry, quotation marks. And here is our macroscopic. And to you and me, this is what we would actually see under a microscope. But look at these beautiful flat patterns. And this is a manifestation of these flat patterns on the atomic level. So what happens? Well, they work together. The sodium donates to the chlorine. The chlorine becomes an anion, the sodium becomes a cation, and they form these beautiful crystal lattices.